Thank you, Mohsen. Am I audible at the end? Okay. Hi, so I'm Gautam, and this is a work that I did jointly with Casey from Cambridge and Kapil and Suresh from Purdue. So what I'm going to talk about today are applications with replicated shared state. So these are the applications whose state is shared across multiple machines or connected devices, and each machine is said to have contain a replica of the state. And users interact with the application through one of the replicas. And these replicas can often be geo-distributed. They can be present at various geographically diverse locations across the globe. This architecture is quite common among large-scale web applications such as Facebook or Amazon and so on. But for the sake of example, I'm going to focus on a simple e-banking application that allows shared bank accounts. Right? Let's say we have a shared bank account shared between, let's say, Alice, Bob, and Cheryl. And the bank account has initial balance of $10. And both all Alice, Bob, and Cheryl update the bank account through ATMs that are present at different locations. So let's say Alice initially sees the the balance of $10 and performs a withdrawal of 2, reading 10 and writing 8. Since it's it's very expensive to do geographic coordination among all the ATMs. The application would commit Alice's write locally immediately and then lazily propagate or asynchronously propagate the write to other replicas, which means that meanwhile, while Alice was doing withdraw, Cheryl can also do her own withdrawal of $3, reading 10 and writing 7, and Bob can also perform a deposit, reading 10 and writing 12. So, and when these writes are eventually propagated and applied at different orders at different replicas, so the balance at the various replicas may contain, may diverge and may contain different values, and moreover, the writes may get lost in the process. So here, while Alice sees the balance of 8, Cheryl sees 7, and Bob sees 12. So the key takeaway from this example is that if you try to define the replicated shared state in terms of low-level effects such as reads and writes, we end up with lack of convergence and lost writes. Right. So, taking this observation, few folks have defined, have tried to lift the abstraction at which replicated shared state is defined. Basically, the observation is if you can define the replicated shared state in terms of high-level data types with commutative operations, which are called, let's say, commutative replicated data types. So you can in fact get convergence. This is because commutative operations can be applied in any order and state eventually converges. So here in the context of the current example, let's say we have a balance which is implemented as a, let's say, integer CRDT, integer commutative replicated type. Alice performs a withdrawal of 2, but instead of propagating the write update, we generate an effect, a high-level effect tagged withdraw, which is essentially a state transformer. The interpretation is a function that transforms a state to a different state, here balance to balance minus 2. And likewise, so this is an effect. When Bob performs a deposit of $2, the effect gets generated, the deposit effect gets generated, which is also a high-level effect, a function. Likewise with Cheryl, a withdrawal of $3 will generate a new high-level effect. So when these effects are propagated to various replicas and applied in different orders, since add and subtract commute, we end up with the same balance at all the replicas, right? So this is great. So this solves the problem of divergence. And because of the utility of convergence, there are multiple CRDTs have been defined which are useful in the context of various applications. So commutativity definitely guarantee convergence, but is it enough? Is commutativity enough to ensure the correctness of applications? So unsurprisingly, it's not. So convergent state can still violate high-level application level invariance. So let's say our banking application has this high-level invariant that says the balance must be greater than or equal to 0. So let's consider a scenario where we have, let's say, 2 replicas of the balance. Alice connects to replica 1, performs a withdrawal of 1, and Bob independently connects to replica 2 and performs a withdrawal of 1. So both withdrawals do not see each other. So both see the balance of 1 and hence they succeed. But when the state eventually converges, we end up reading the balance as -1. Right? So this is an anomaly that has happened due to concurrency essentially. Right? A more subtle anomaly happens because of the fine print in the convergence. Since the convergence is essentially eventual, while the state hasn't yet converged, it's possible to see transient falls. So the example on the right-hand side, the scenario on the right-hand side demonstrates this process. So let's say we have two replicas initially balanced as 0 on the both ends. Alice performs a deposit of 1. Bob can see the deposit and performs the withdraw. So withdraw succeeds because Bob can see the deposit. But Cheryl, due to anomalies in the message delivery, due to the differences in how messages are delivered, Cheryl gets to see Bob's withdraw but not Alice's deposit. So she ends up concluding that the balance is in fact -1. So these scenarios demonstrate that invariants can be violated or they seem to be violated even when the state of the application converges, right? Um, so and this is not, the high-level invariants are pretty common among applications. Although the bank account example that I've demonstrated is arguably a toy example, we have in the real applications invariants such as primary key constraints. For example, a person's table may require the unique ID. Likewise, differential integrity or foreign key constraints between various tables. Or in the context of more involved applications, such as the applications defined by TPC, which is a standard database benchmarking benchmark. So we have TPCC, which is a warehouse application, which requires per district order IDs to be unique and sequential, and TPC, which is a brokerage application, which requires a brokerage count of the trades to match the firm's the brokerage firm's tally of the trade. So the takeaway is that the high-level applications are pretty high-level invariants are pretty common among applications, and they can be violated even when the state converges. Right. So what's the fix? So the straightforward fix that we can think of is to extend this commutativity or CRDTs with concurrency control. Right. So we can extend CRDTs with just enough concurrency control to prevent high-level invariant violations. But how much is just enough? Right. So in particular, concurrency control can occur in various forms, and it can be applied to various operations in the application. So in which among the application's operations require concurrency control, and in what form is a tricky question. Especially when we think of concurrency control, we usually think of this high-level criterion such as serializability or linearizability and so on. But it so turns out that there's a host of concurrency control mechanisms which are commonly referred to as consistency models, and they can often be partially ordered. They can be shown as a lattice, right? So if we ask application developer to pick the appropriate one among this host of consistency levels, developing a replicated application becomes even more trickier, right? So ideally, we require a system to make these decisions, but not the programmer, right? So in other words, we need a way to automatically reason about these application semantics in the context of various consistency models. So that's what we propose in the paper. We propose a system called Q9 that is basically at its core a bounded verification system. So Q9 tries to verify these replicated applications under a concurrency bound, and in the process it discovers anomalies, also proposes program repeats, and gives the bounded guarantees on to whatever bound it has verified the application. Right. So as I mentioned, at the core of Q9 it is a bounded verification approach. So the verification depends on the observation that replication bugs have these representative anomalies that manifest under a small concurrency bound, right? So when I say concurrency bound, it is actually a bound on the number of concurrent effects. I'll explain it with help of an example. Let's say we have two replicas of any application. Let's start with an empty state, right? So there is an operation op that executes at replica R1, generating an effect. So and op gets to witness the empty state. So op here is, for example, a withdraw or a deposit operation, and the type signature essentially says that it takes some argument and the current state and produces an effect which is essentially a state transformer, right? So E is an effect which we represent with capital letters, and it's a state transformer, sigma to sigma. So when op1 generates an effect E1, E1 gets applied to replica R1. Likewise, let's say we have another operation op2 executing at replica 2. E2 gets applied to R2, and eventually the effects are asynchronously propagated to other replicas, and both E2 and E1 gets applied to different replicas, albeit in different order, but the order doesn't matter because we've assumed them to be commutative. Now let's say there is a new there are new operations op3 and op4 executing at replicas R1 and R2, generating effects. So op3 witnesses the effect of applying E2 and E1 to the empty set. Likewise, op4 witnesses the effect of applying E1 and E2. So we say effects E2 and E1 are visible to op3 and also op4, right? So E3 and E4 get added to R1 and R2. Now at this particular snapshot of the system, we have a certain common prefix between both the replicas, which consists of effects E1 and E2, and a replica specific suffix, which consists of concurrent effects. So a concurrent effect is essentially an effect that is not present on at least one replica. Right? So we have E3 and E4 as concurrent effects. So if we generalize this scenario, we have E1 to EK as concurrent effects. So let's say distributed between replica R1 and R2. So by the way, the indexes does not matter. The E1 and E2 do not denote the sequential order. They're just indices. So here in this particular scenario, we have K concurrent effects, and K is what we call as a concurrency bound, right? Right. So the verification problem is about verifying any given operation of the application under assuming a precondition P and proving that after the operation executes, the postcondition Q is valid. So this can be written as a triple. So the semantics of triple, I'll explain the semantics of the triple now. So let's say we have ignore R2 for a while. Let's consider replica R1. We have fxe1 to ej at replica R1 and some prefix, some common prefix. So let's consider what is the state at R1. So it is basically fxe1 to ej applied to the common prefix, right? So let's call it delta 1. Now let's say we have an operation that executes at replica 1 that sees delta 1 and generates an effect E, and E gets added to the replica immediately. So the post state after we add the effect E is essentially E applied to the pre-state delta 1, right? So in the context of this replica, the verification judgment is essentially showing that when the precondition is initially valid, we execute the operation, then the post condition is valid immediately. So this is no different from a sequential verification process. However, it is also incumbent on the operation to show that when the effect E gets applied at a remote replica, the post condition is nonetheless valid. So in the remote replica R2 here, R2 is remote for effect E because the origin of E is replica R1. So the pre-state at the remote replica is ej plus 1 to ek applied over the common prefix, and the post state is the state after we apply E. So the verification condition at the remote replica is essentially assumes that initial states are valid and tries to prove that at the remote replica the final state after applying the effect is also valid. So what we refer to the first one on the left hand side as local correctness condition, and the verification condition on the right hand side as the remote correctness condition, right? So this essentially captures what it means to verify any operation of an application, replicated application under a concurrency bound. So here we have finite number of effects, so hence it's a verification under concurrency bound. However, this is fine in theory, but in practice, this verification conditions actually capture a whole state space of configurations. So for example, we can have any number of replicas, although I've shown just 2 for the sake of the example. And among the given effects, these effects can be distributed among these replicas in any proportion, right? So there's a whole host of configurations. So in general, it's inefficient to try to verify try to do verification as defined by the verification condition naively. So the observation we make is that we can in fact lift the level of abstraction for verification to the level that abstracts away the low-level artifacts such as replicas and distribution between replicas and so on. So our observation is that if we choose a sufficiently expressive axiomatic framework, we can abstract away the low-level details and succinctly express executions, and then we can make use of symbolic techniques to reason about these executions. So the axiomatic framework we choose is consists of certain relations, which is akin to weak memory relations such as reads from and coherence order and so on. So these are analogous relations in the context of weak consistency. And to demonstrate how this happens, I'll consider verification of bounded verification of withdraw with a small bound with k equal to 1. Let's say we want to show that initially get balance returns non-negative balance, and after withdraw executes, we want to show that the get balance still returns non-negative balance. So since we have chosen k as 1, we have certain pre-state, a common prefix state b, which is greater than 0. Since k equal to 1, we have one concurrent effect. Now observe that this actually represents two different replica states. There are two possible replica states with this configuration, with the replica that contains E1 or that may not contain E1, since bound is at most k. So now let's say we in the pre-state we are trying to show that get balance withdraw is safe, assuming that in the pre-state get balance returns non-negative balance. So let's consider get balance in the pre-state. So it witnesses B and some subset of the fx E1, since it can execute on any of the replicas. So any subset of E1 would represent the replica state that it sees, right? So for the sake of this demonstration, let's say it produces an effect EG. So E1 may be visible to EG, in which case we write vis E1 EG, or E1 may not be visible to EG, in which case we write not of vis E1 EG, right? Now using this formalism, we can express what the result of get balance, right? So the get balance evaluates to B plus if it sees E1 EG and E1 is a deposit, then it adds A. Likewise, if it sees E1 and E1 is withdraw, then it adds minus A, otherwise it adds 0. So notice that this captures all possible balances in the pre-state without making any reference to how many replicas are present or what effects are present on what replicas. So this is the intuition we apply to translate this verification condition that I've shown previously into something more tractable, something more that uses the axiomatic relations that I've shown. So it's not important to actually go through this verification condition, but it's important to observe that it makes no reference to replicas or low-level artifacts. So this is a verification condition on axiomatic executions. So VC on axiomatic executions can be dispatched to a solver, an SMT solver, and solver will give us, in case if the verification condition is invalid, it gives us counterexamples, which counterexamples here in this case give assignments to the visibility relations and concretize the effects such as E1 and EG and so on. So these counterexamples are represented graphically on the right hand side of the slide. So these examples, these abstract counterexamples, in fact, correspond one-to-one to the initial anomalies that I've shown at the beginning of the presentation. I'm in interest of time, I'm not going to go through the program repair in detail. But the program repair is actually, at high level, program repair is done by iteratively strengthening the consistency models. So what we observe is that the consistency models or various concurrency control mechanisms, they can be expressed at a high level as constraints on these axiomatic executions. Since we can translate programs to axiomatic executions, and we have consistency models also expressed as constraints on axiomatic executions, so we can reason about these two in conjunction to understand or to find out what is the weakest consistency level at which we can prevent a particular anomaly or verify an application under a given bound. So this slide in particular shows various common popular consistency models that were expressed using these relations. All right. So moving to the evaluation, so we actually, while evaluating Q9, the Q9 is a tool we have implemented this approach in. And to evaluate Q9, we actually have chosen certain set of database applications, benchmarks and standard applications, and tried to port them to the weakly consistent or weakly replicated setting. So these include certain applications, standard applications such as Rubus and Pisandra and so on, and also standard database benchmarks I've talked about previously, just TPCC and TPCE. So Q9 was able to automatically find counterexamples demonstrating invariant violations for these applications, and was also able to find the weakest consistency model to prevent each such violation. And it can do so in a reasonable amount of time. So the column highlighted there shows the maximum amount of time it took for Q9 to find an anomaly for all the applications. So the largest time taken was for TPCE, which was under 2 minutes. So among the other details in the table, so the column number 3 shows that various applications have different number of transactions. So the approach actually generalizes to transactions and the corresponding isolation levels. And there are certain applications which have been, such as e-banking in Twitter, etc., that were verified with a very relaxed concurrency bounds, which is 50 and 60. So this is really high bounds. And the well-known database benchmarks such as TPCC and TPCE also exhibit anomalies when ported to this weakly consistent setting. So in summary, we do bounded verification at a higher level of abstraction for these weakly consistent programs, and it turns out it actually scales to real-world weakly consistent programs. And this approach is particularly useful in the context of in assisting programmers while porting legacy database applications to NewSQL and NoSQL stores. So that's all I have.
Okay, questions? Yeah, I have a question.
Yeah.
So it seems like this unrolling to K is because you don't want to write rely and guarantee conditions for each operation. If you do that, probably you can generalize whole logic to reason about these systems. Is that right?
That's right. So the whole idea here is to avoid any sort of annotation burden. So when we can find these anomalies with a fixed bound under a fixed bound, so it basically at least serves as a triage to first of all fix the bugs in the application, and later on you can try to do rely and guarantee based reasoning to actually verify the application for unbounded. Thanks.
If I might propose perhaps the wrong level of abstraction, full convergence for distributed programs under CRDTs kind of requires you to treat the whole of program state as a CRDT. Every conditional branch that you take after reading from a CRDT may observe a value that in the final sequentialization never actually occurs, or at least can't occur at that point in the program. Have you thought about what it would be like to try to pepper assertions so far through the code base that you actually get full convergence and strong eventual consistency?
So could you elaborate on that? I didn't quite get it.
Sure. Sorry.
Yeah.
As an example, we can imagine a world where we have a counter and it is initialized at 0.
Right.
And the first person tests to see if it's 1, and if so, adds 7. And the second person tests to see if it's 0 and adds 1. The second person just adds 1. But the final sequentialization means the first person wins, so we see 7, then 1 in the ultimate God's eye view. But
that's right. So
the 7 should have never been added.
Yeah. So the convergence as a criterion ignores it does not guarantee any linear order of operations among various concurrently submitted operations, right? So in that sense, convergence is actually a very weak condition. And that is why we have this concept of application level invariance. So the idea is, of course, you can try to, there is this high level criterion on serializability or sequential consistency, which applies for every application. But maybe that's not useful, that's not required for all the applications, right? So the idea is if you can capture what is needed beyond convergence as an application level invariant, then you can, in fact, verify using something like bounded verification.
I guess I was wondering if you did actually put enough verification conditions so that for all the observation points you cared about, you really did get this much consistency. How much would that slow your scaling?
How much does the behavior deviate from sequential consistency? So that depends on the actual runtime setting, right? So for under let's say weaker forms of consistency such as eventual consistency, we can always come up with a counterexample that where we do not have a linear order of all the operations. Yeah, sure.
May I ask another question?
Sure.
So in your previous work from your group, Quella, you had a technique to find the weakest memory model that can keep invariants, right? And it seems very similar to the repair that you are talking about here. What is the difference?
So the difference from there to here is the change. It's the transition from contracts, which are low-level consistency specifications that are expressed on axiomatic traces, to high-level conditions such as balance greater than 0 or referential integrity and so on. So the key here is that programmer can be completely oblivious of any of the machine-level consistency models. The programmer can just write the high-level invariant and the program, and whatever contract generation and everything happens internally. So the programmer does not have to declare contracts as we have did in Quillian.